In this video, I'm going to give a very brief introduction to intermediate code and its use in compilers. So the first question to address is, what is intermediate code or an intermediate language? And as the name suggests, an intermediate language is just that. It's a language that's intermediate between the source language and the target language. So keep in mind what a compiler does. So a compiler takes a program written in some source language, and it provides a translation of that program into some target language. And so in this class, for example, where often our source language is COOL and our target language is MIPS assembly code. Now, an intermediate language actually lives in between these two, and a compiler that uses an intermediate language will first translate its source language into the intermediate language, and then later translate the code in the intermediate language into the target language. And you might wonder, well, why make life so difficult? Why do something in two steps if you can do it in one step? And it turns out that for many purposes, this intermediate level here is actually quite useful, precisely because it provides an intermediate level of abstraction. So in particular, the intermediate language might have more details in it than the source language. So for example, if we want to optimize register usage, a source language like COOL has no notion of registers at the source level, and so there's no way to even express the kinds of optimizations you might want to do with registers. So an intermediate language that exposes that amount of detail, at least has registers in it, would allow you to talk about and write algorithms that could try to improve the use of registers in the program. On the other hand, the intermediate language will also have fewer details than the target. And so it might be, for example, that the intermediate language is a little bit above the level of the particular instruction set of a particular machine, and therefore it's easier to retarget that intermediate level of code to lots of different kinds of machines, precisely because it doesn't have all the grubby details in it of a particular machine. And experience has shown that this is actually a pretty good idea to have an intermediate language, and almost all compilers have an intermediate language, in fact, in their implementation, and some compilers have more than one. Some compilers actually translate through an entire series of intermediate languages between the source and the target language. Now, we're only going to consider one intermediate language for the rest of this course. The kind of intermediate language we're going to look at is going to be a high-level assembly. And so, as I suggested on the previous slide, this language is going to use register names, but it will have an unlimited number, so we can use any number of registers that we like. We're not bound to 32 or 64 registers. The control structures will look a lot like assembly language. In particular, there will be explicit jumps and labels on instructions. And the language will also have opcodes in it, so it look like assembly language level opcodes, but some of these opcodes will be higher level. So for example, we might have an opcode called push, and a push would end up translating into several concrete assembly language instructions for a particular target machine. In the intermediate code that we'll be looking at, every instruction will have one of two forms. It will either be a binary operation, or it will be a unary operation. And always, the arguments on the right-hand side, in this case the y and the z, will be either registers or constants. They could also be immediate values. And this is a very, very common form of intermediate code. It's so widely used, and it's so widely used it actually has a name. It's called 3 address code, because every instruction has at most 3 addresses in it, 2 arguments, at most 2 arguments, and then a destination. Now, to see that this code is actually low level, notice that higher level expressions that involve multiple operations will have to be translated into a sequence of instructions that do only one operation at a time. So for example, if I have the expression x plus y times z, and let me put in parens here to show the association, so the times binds more tightly than the plus, we're going to have to, this can't be written directly in an intermediate language of this form. Instead, we would have to write it something like the following. We'd have to first compute y times z and assign that to a new register or a temporary or a new register T1 to hold the intermediate value. And then we would have to use T1 to compute x plus T1, which of course is the value of the entire expression, and that would end up getting stored in another register. And notice that one effect of forcing you to use only one operation at a time, basically you can do one primitive operation at a time, and then the result of that has to be stored in a register. One effect of that is to give every sub-expression of the program a name. So if I look back at this expression here, I see, like y times z is anonymous. That in this expression, x plus y times z, the expression y times z itself doesn't have a name. And by rewriting it like this, I actually name that intermediate result. So again, just to summarize this point, one consequence of having to write out compound expressions as a sequence of instructions that do a single operation at a time is that every intermediate value will be given its own name. Generating intermediate code is very similar to generating assembly code. And we're not going to go into this in any detail because it is so similar, but I will sketch it for you briefly. The main difference between generating assembly code and generating intermediate code is that we can use any number of registers in an intermediate language to hold intermediate results. To generate intermediate code, we could write a function called igen for intermediate code generation that takes two arguments. It takes the expression for which we're generating code, and it takes the register into which the result of that expression should be stored. And to give you just one example, and this is the only example that I'll do, let's take a look at generating intermediate code for a plus expression. So I want to generate code for E1 plus E2, and I want the result of that to be stored in the register T. Okay, so the first thing I'm going to do is I'm going to generate code for the sub-expressions, and I need some place to store the results of the sub-expressions, so I'm just going to make up new register names for those results. So I'll generate code for E1 and store that in some register T1, and I'll generate code for E2 and I'll store the result of that in some register T2, and then we can just compute the sum. So T will be equal to the sum of T1 and T2, and notice that this is a 3-address instruction. So we're sticking to the rules here and only using 3-address instructions in our intermediate code generator. And also notice that because we have an unlimited number of registers, this actually leads to very simple code generation of intermediate code. In fact, it's even a little bit simpler than generating code for a stack machine. Recall that in a stack machine, we had to save the intermediate result here of E1 on the stack, and that involved more than one instruction to actually push the result and adjust the stack pointer and things like that. And here we can just save it in a register and then just use that register name later on. So that is actually all I have to say about intermediate code for this course. You should be able to use intermediate code at the level in which we're going to be using it in lectures. In future videos, we'll actually be looking at intermediate code quite a bit and using it especially to express certain kinds of optimizations. You should also be able to write simple intermediate code programs, and you should be able to write algorithms that work on intermediate code. But I'm not going to expect you to know how to generate intermediate code because we're not going to discuss it any further. And quite frankly, it doesn't introduce any new ideas. It's really just a variation on the code generation ideas that we've already discussed in quite a bit of detail.